Today I'll be introducing the topic of data flow computing and explaining how it represents a shift in computing paradigms. For many decades, most computers have been based on von Neumann model where programs are executed step by step using a program counter. This model has served us well, but with rapid growth of applications like AI, scientific simulations, and big data analytics, we now need systems that are faster, more parallel, and energy efficient. The VLSI technologies moved most towards the nanoscale processors, and the researchers have explored new architecture. One of that is data flow computer. Unlike traditional machines, in data flow system, instructions are executed as soon as the required data is available, not in a massive fixed sequence. This leads to massive parallelism, which removes the von Neumann bottleneck and makes computing much more power efficient. In this session, we will explain about the basics of data flow computers and how they differ from von Neumann systems and why they are so important for the future of the computing.
Role of VLSI in data flow. VLSI lets us fit millions or even billions of small processing units on one chip. This is important for data flow computers because they work best with lots of tiny processors running parallel. Speed and power efficient. By improving transfer distance, VLSI makes chips run faster and use less power for its operation. VLSI can put entire data flow diagram, special processing unit, and memory all on the same chip. This reduces delay and makes the system more efficient. And the limitations of VLSI. As chips get smaller, they produce more heat in a small space, making cooling difficult. Power leakage. At very small size, transistors can leak electricity even when they are off, wasting energy. Quantum effects. At nanoscale, quantum behavior like electrons tunneling can cause error and make chip less reliable.
Why migrate to nanoscale? As the chip shrinks, we pack more cores in the same space, enabling bed parallel execution and high performance per watt. This high performance helps us in exploring demands on AI, machine learning, scaling the computation, and cloud workloads, where speed is an essential aren't optional. The essential smaller nodes allows us to build complex, efficient data flows machines that weren't possible before. This migration can be achieved using some of the technologies like FineNet, GAFET, CarbonFET, and 3D ICs. FineFET provides better gateway control and reduces the leakages. And FineFET pushes the scale even furthermore below 5 nanometers. And carbon nanotube FETs offer extremely high speed with ultra low power. And 3D ICs uses vertical stack to cut interconnect length and boost the performance. Still now we have saw all the pros of nanoscale technology, but there are some of the consequences which should be addressed. The major two consequences are thermal management and manufacturing defect. Coming to the thermal management, as we know, small space is occupied with more number of transistors and ICs, which will produce lot more amount of heat, which should be managed for higher performances. Managing heat in separate transistors is way more easier when compared to nanoscaling. So this should be addressed, and they are working on this and further processes. And when it comes to manufacturing, nanoscales, like the transistor will be in an atom size. If there is a small mistake, the entire nanoscale will be like nanoscale chip will be under damage. So manufacturing is also plays a vital role, and which is a crucial thing in manufacturing. Still now, experts are researching over it how to make this more efficient and how to manage the thermal more efficiently to increase the performance and making it in live.